recording. All right, so we'll be moving on to another important aspect of power electronics, and we'll be looking at the AC/DC conversion. That's rectification. All right, so there are three categories that we'll be looking at. We're looking at the single phase, that's for half wave rectification, and the single phase as a full wave rectification, and then we will look at the three phase rectification. For the single phase, right, there are three main headings that we'll be focusing on: uncontrolled, and that's for resistive load, resistive and inductive load, resistive and capacitive load. Right, when we say uncontrolled, right, based on our last class that we have, this is referring to the diode, right? That's uncontrolled rectification. However, on the other hand, for controlled rectification, you see when we look at things like your SCR, your TRIAC, and so on, these are controlled. These devices can enable controlled rectification. We'll be looking also at the function of our freewheeling diode, right? So when we look at the full wave rectification, we'll be looking at the same as in the case of the single phase half wave rectifier, where we're looking at it for uncontrolled, controlled, and then we'll be looking also at two modes of operation, that's in continuous and discontinuous current mode. For three phase rectifiers, we have the controlled and uncontrolled aspects of it. So we'll be focusing on those two aspects. All right, so we'll start with our definition of our rectifier. Our rectifier is just a way, a means by which we are able to convert alternating current, that's from our mains to direct current, when we use diodes or any of the devices that we're able to have control over the output, right? Things like thyristors that will enable the output voltage to vary as we change the firing angle, right? So thyristors like TRIAC, your SCR, any of those devices, we can change the average output voltage by varying the firing angle. So what we have here is just a block diagram, right? So it's a rectifier, we have AC input and our DC output, right? So the input, as I mentioned earlier on, it can be single phase or multi-phase, right? So we'll look at the three phase for this course, right? And the output, right, it can be fixed or it can be variable, and of course we have applications of this, right? The DC motor drives, battery chargers, DC supply, and their high voltage DC, and their welder. So the first one, very simple case with your with your control rectification, we just have a diode and a resistor as our load. As you can see here, the input waveform, right, sinusoidal. However, as it passes through the diode, the negative portions of this wave, this signal is removed, so we only have the positive cycles. Right? In the last class, we calculate this value. I think we proved that the average output voltage is given by the peak voltage divided by pi, right? So 1 over pi, that's just 0.318, right? So that's how we move from this peak voltage or maximum voltage over pi to 0.318. First, this average, how we calculate it, we just taking the sum of all the points, right? And we using calculus, right? So the integral gives us the sum, right? So we're taking all the points, so that's the sum, and our limits is between 0 and pi. Because if we look over one period, right? So this a period would come up to this point, right? So between here is just 0 right here. So effectively we sum in between 0 and pi. That's why this limit is between 0 and pi. And of course, the average, we're taking it over the period. Yeah, of course, in this case, our period is 2 pi, so divide by 2 pi. Of course, when the dust is settled, after you have gone through this integration, you should arrive at this value. Now, in the case of the RMS voltage, that's the root mean square. So you're going to take the mean, the square of the mean, and then take the square root. Right? So you would have the mean here. Right? This would be the expression for your mean. You're going to square it, and then you're going to take the square root. All right, so that should come to about 0.5 of the peak. I think I've gone through the first proof with you, so maybe I can just quickly show you in the case of this one. Let's do a quick all right, so they're saying for that kind, the RMS voltage is equal to the sum. I would say it is between 0 and pi, and because it is sinusoidal, it's just equal to Vm sine omega t, and we're going to, so that's Vm sine omega t, right? So we need to square this, and we are integrating with respect to d omega t, and we're taking the average over one cycle. So that's 1 divided by 2 pi. All right, so we can go through and square this. So what do we have here? That would be Vm square over 2 pi. And we have our square here. This is between 0 and pi sine square omega t. All right, integrate sine square, what do you get? Huh? Hello, class?
Sir,
When you integrate sine square, what you get?
we get a half cos 2 WT.
A half cos 2,
WT.
2,
Yes, sir.
that's what you get?
Yes, sir. Using the trig identity.
Using the trig identity. All right, let's, all right, so we're going to use a trig identity, and that would be that this your sine square omega t, what would that be equal to? That would be equal to
half cos.
hmm?
Half cos WT. Half cos WT.
That would be equal to a half of 1 minus 2 cosine 2 omega t. Is that correct? Right. So in other words, we just have a half minus cosine 2 omega t. All right. So this is what we'll substitute and do our integration. All right. So substituting this. All right. So I take this out. Then I take the half. So that's Vm square over 4 pi and this is respect to the omega t. All right, when we integrate that, what do we get? What do we get?
Cos minus.
All right, this should now be more familiar. This will be what? Integrate. This is 1, right? integrate that constant, what do we get?
Omega t
Right, we get omega t
minus
and 2 cosine 2 omega t, what do we get?
4 sine omega 2. Sorry, it's 4 sine 2 omega 2.
You get 4 sine 2 omega t. And what would be the sign? Is it a positive?
No, sorry, negative.
So, all right. You're saying minus minus, or this should just be minus?
Yeah, minus.
Huh? Minus minus?
No, just minus.
Okay. Just minus. All right. So need to substitute the values, and what do you get? All right, so it's clear that you'll get 0 on one side and you'll get pi. We left out something at the top, right? The square root. Take the square root of all of this. 12 square root, and here 9. All right, so this is going to be equal to, substitute pi, the sign part will disappear, and we only have pi here, the 0, all of it will go away. So we basically have square root of Vm square over 4 pi times pi, right? So, and that is going to leave us with
Vm
thus the peak voltage over 2, right? Or thus a half of the peak voltage. So that's how we're able to calculate this. Right? So that's the idea. So with power electronics, hope you keep your mathematical skills, right? Because you will need to be able to apply it here. All right, so when we look at the case with an inductor, right? So we've now finished that. This is with simple resistor, right? Very simple case, no problem. Right now with the inductor, right? So it's our circuit, and we're going to apply Kirchhoff's voltage law around this loop, right? So the input, again, this is Vm sine omega t, this sinusoidal input. So going around, we have the voltage up across the resistor, we have voltage up across our inductor, right? And of course, this is equal to the input. So that's how we get this expression, right? Very simple, right? So your input plus the sum of the algebraic sum of the voltage drop across your resistor and your inductor. Right, so what's the voltage drop across your resistor? We have a current I that is flowing, right? So that would just be equal to I times R. Of course, this I is an alternating current, so I write it as a function of omega t, right? So I times R. How about the voltage drop across the inductor? Right, so we know that it's going to be L di dt. Okay, so that's what we write here. Now, what do we have here? Right, this is a first order differential equation, right? And we can let a possible solution be some force response for the current plus the natural response for the current. Right, so this is a possible solution that we are proposing. Of course, the force response is just given by this expression, right, where we just divide by the impedance, right? So this here from this, right? You see that the solution is the force response plus the natural response, right? So our current, right, is just the peak divided by the impedance, right? And we'll have some phase shift here, right? Because it's impedance that we're talking about, where we're inductor in the circuit. So a phase shift, let's call it theta, right? So we know how to calculate our impedance. It's just given by the square root of the square of our resistance and the square of 2 pi FL, right? So 2 pi F is our omega part of this expression. And of course, you should recognize that the angle so formed will just be the tan inverse of omega L over R. That's the frequency times the inductance divided by the resistance. Right, so this part is not new to you. You have studied it when you did circuits and networks. Now, the natural response, that is when we're going to take this source and let it equal to 0. Right, so we're going to set this equal to 0 and then determine the natural response. So that's all we're doing here. If you recall, the int is just equal to the voltage drop across the resistor and the voltage drop across the inductor, and that's the input. So now we set the input equal to 0, and then we're going to attempt to solve this first order differential equation. All right, so we can let a solution be for the natural response some constant A multiplied by the exponent of E, exponent E, the minus omega t over omega tau, where omega tau here is just the time constant given by the inductance over the resistance. So now we can substitute this into the expression, right? So our current, our solution, this response and the natural response of our current. Earlier we determined that the force response is given by this part of the expression, that's Vm over Z multiplied by sine of omega t minus theta, and the natural response, we can substitute it there, right? It's just equal to A exponent to minus omega t over omega tau. Now, how do we actually solve this expression, right? We can look at it when the inductor current, when it's going to zero, all right? We need to find out what is, so that is why we're solving. What is A, right? So let's look at when the current in the inductor, when it's approaching zero, right? So we set the current, right? This current, we set this equal to 0, or omega t, set it equal to 0, right? So omega t in the expression equal to 0. And when the dust is settled, we rearrange, making A the subject of the formula, right? This is what we end up having, just the peak voltage divided by the impedance multiplied by sine theta. All right, so now we can substitute the values. Now that we know what A is, we can substitute back into the expression, right? So as I can see here, the A, we have the Vm over Z, and the A has a Vm over Z. So we can factor out that part of the expression, right? So we have our sine into omega t minus theta, and plus, that would be plus sine theta, that's the A that we substitute, right? Sine theta, and multiplied by E omega t over omega tau. So that's the expression for our current in the solution. All right, so we look at the waveform. These are the waveform. So initially, we have this wave here that we're looking at. So this is our input, but you'll notice that for the current, there is a shift. There's a shift. And why is this so? This is because of the inductor that is in the circuit, right? So there's a phase shift that is observed, right, between the voltage and the current waveform, right? So before, when we studied the rectification with only a resistive load, we saw that the voltage and the current, they were in phase. However, with your inductor, right, or your inductive load with a resistive load, right, you observe this kind of phase shift. Also, this point at which the current through the diode goes to 0, we refer to this as our beta, right? So this is beta. But there might be something a bit strange. This is a diode, and I'm observing some negative spikes in the output waveform, right? As you can see here in the output, right? So up to this point, we have our voltage. If you look at it right here, our voltage. However, it seemed to have conducted a bit longer into the negative region, right? At this point where it goes to 0. Can you tell me why? Can you make a guess why this is the case?
Diode breakdown, sir.
Why are we observing this? Why? Diode breakdown? Any other answer?
Or the inductor.
What about the inductor?
The positive. How should I explain it? The inductor, because it opposes change, is going to
Yeah,
conduct.
all right, yes, that's very right. All right, so if you look at what is happening right here, in this interval, the current is now decreasing, right? We have a current decreasing. It's positive, but it's not going to decrease. So the inductor is going to react to this. So what you're going to have happening is that you have a negative voltage, right? So here it was positive. So in response to it, we have a negative voltage because of a decrease in current, right? So that is what is happening here. So that's why we have this peak in the negative direction. So it has nothing to do with the diode breaking down. It's because of the inductive load that is in the circuit, right? So the other waveforms are pretty much straightforward. If we look at the voltage waveform across the resistor, as I can see, it will basically follow the current waveform in the circuit, right? Pretty much follow it. And the voltage across the inductor will pretty much mimic what we have at the output, right? So this output waveform very much similar to the voltage across the inductor waveform. Any questions? All right. Right, so I made a point here that it's the V LDI that was responsible for this negative section of the waveform. All right, so that beta that I spoke to you about a short while ago, right? The point at which the current flowing through the diode equals to 0. At that point, is referred as our extinction angle. So we're going to determine it. So remember this formula that we have developed. So we're now going to substitute beta into this expression to determine the extinction angle. So when this equals to 0, then we can determine our value of theta. Now, this beta, we have to, this is the equation that is resulted. How do we solve this? right? So one method is numerically, right? So you can use your computer to actually solve this expression. You have probably done numerical analysis, right? So you can use that method to solve for your beta here. All right. There's another method that I will use. I'll use a graphical technique. Since in your exams you'll not be using your computer, right? So I will show you a graphical technique that can be used to obtain your extinction angle. All right, so just to summarize, in the case of your rectifier with resistive inductive load, right, the current that will be flowing through can be given by this expression that I've shown here. And this is for omega t, that is between 0 and the extinction angle, right? So if you look at the curve, right, so your current, right, this is where the equation is valid. There are two parts between 0 and beta, right? That will give you the first part. Otherwise, what you're seeing, it is 0, right? So it is 0. So that is why it is expressed like that. So between 0 and beta, it is governed by this expression. Otherwise, it is 0, right? As we have seen here. The current between 0 and beta. Otherwise, it is 0. All right, we can find things like RMS current and the power. All right, so we look at RMS, the concept is not different, it's very much similar. So if we're going to look at the average DC current, right? If we look at and go back to the waveform, what's the average current here? We need to find the sum between your 0 and your beta, right? Because between here, or period here, would be between that point and that point. All right, so this right here is a 0. We sum all the points, or limits will have to be between 0 and beta, right? Because here is just 0. So we sum, right, or current between 0 and beta, and we divide by the period, right? The period is 2 pi, as you can see, right? So here, between here and here, that's just 2 pi, right? So that's our average current. How about the RMS, the root mean square? We're going to take this current, we're going to square it, and then take the square root, right? So you can do that for your homework. Let's work this out. And important to note, right? You get some questions to ask, what is the power absorbed by the load, right? The power absorbed by the load is given by the square of the RMS current multiplied by the resistance. Very important to note that it's the square of the RMS current multiplied by the resistance. So in this kind of circuit, right, the inductor, right, these are wattless devices, right? So where you have the loss is going to be in the resistive element. Right, so sometimes we're asked to calculate the power factor in the circuit, right? So ratio true power to apparent power, right? That's our power factor. Right, so apparent power S, right, is given by the RMS voltage, right? Input RMS voltage multiplied by the RMS current, right? So we can substitute this formula where we have true power or real power divided by the the product of the input voltage and current, right? With their RMS values. So I finish here. So that's it for the case of the resistive inductive load for uncontrolled rectification. We'll now look at the case of the resistive capacitive load for uncontrolled rectification. With this one, you're perhaps somewhat familiar with it, right? So that's the circuit that we have. As you can see, we have our capacitor here in parallel with our load. Now, what is happening? We have our input AC is going to allow conduction in one direction, that's in the positive cycle. You're going to have the capacitor charging at some point, and as it decreases, as this decreases, then the capacitor is going to discharge through the load, the resistive load, right? But that is what you are observing in this waveform here. So we have our maximum, let's say we have our the voltage being at the maximum initially. Then as the voltage decreases, right? So here it charges up in this region, capacitor will charge up, and then as the voltage starts to decrease, the capacitor will discharge. So that is what you observe in this region, the capacitor discharging, and then as it goes back to the positive cycle, the capacitor will charge up, right? So it will charge, and as the voltage decreases, as in this region where I have a voltage decrease, the capacitor is going to discharge, right? So what you have here in this curve is as a result of the charging and discharging of the capacitor, right? So this gives us our output voltage. All right, so as you can see, it will swing between maximum and a minimum here. So this difference is what we refer to as our ripple, right? Difference between a maximum and minimum. Now, if we look at the current that is flowing, when the device, and this is let's say when it reaches a point where the output voltage, the voltage across our capacitor and our resistor are the same as the input voltage, then there will be no current that will be flowing at that point. As I can see here, it will cause this input voltage will cause this capacitor to charge, right? So it will charge up until it is at maximum charge, where it will be maybe about the same voltage as the input voltage. So at that point, we wouldn't have any current flowing through the diode. However, as it as the voltage here decreases, as I can see here, we're going to have a current that will be flowing through the diode, right? So as it discharges in this region, you observe that the current that will be flowing through the diode would be 0 at that point. All right, so we have 2 points on the graph, our alpha and our theta. All right, so if you observe, when this this diode is turned on, right, we have expression that we can use. It's just the Vm sine omega t. That's pretty straightforward here. Vm sine omega t. That's for this portion. Also, in this region, when it is decreasing, that's an exponential decay, right? So that's just the voltage, e to the minus omega t minus this theta divided by omega rc, right? It's for this region where it is discharging. So initially, this part, just Vm sine omega t, thereafter it's discharging, right? So that's why we have this exponential factor in this part of the expression for when the diode turns off, right? So in this region, turns off, no current is flowing, it exponentially decays, right? That's the voltage. All right, now this V theta, that's just Vm sine omega t. All right, so what, let me go to a question here. All right, so how do we find that theta? How do we find that theta? If we go back, at this point, we can use a slope, right? So if we can find the slope, then we will be able to determine the value of theta. Right? So remember there are two functions, right? So just when it is charging, when it reaches its maximum, to when it starts discharging, we can set the two equal, right? Two gradients must be about the same. So that's the idea here. So remember, to find gradient, we can just use this derivative, right? So the first part, right, is Vm sine omega t. How do we find this gradient, right? We just find the first derivative, right? So that's what is done here. First derivative of that Vm sine omega t, and it's just Vm cosine omega t. Also, there's another section, right? This section, right? It's just Vm sine theta e to the minus omega t minus theta over omega rc. We're going to find the first derivative of that expression here, right? So this one is not as simple as this one. You would have to use the rule that that would apply to a function. Let me go back to it, right? Where we have two parts, right? Two parts to actually do this kind of differentiation, right? How you differentiate a function uv, right? So v du, right, plus your u dvu, right? So that's basically what you're doing here, right? So you can do this part for your homework. Just do the differentiation of this. So as we observe, the two slopes must be equal, right? So at this point where we have omega t equal theta, the two slopes must be equal, right? At this point, right at this point, when it reaches its maximum and when it starts to decrease, right? So the two slopes must be equal. So we set the two gradients equal, and then we try to solve the expression, right? So this is a result of this. So Vm cosine omega t, and when we differentiate this one, it comes to this expression. And by rearranging, we have Vm cosine theta over Vm sine omega t, and it's equal to minus 1 over omega rc. Of course, from your trig identities, you know that cosine over sine, that's just 1 over tan, and that's equal to 1 over minus omega rc. And we can write a generalized solution for this, for your tan, right? So that would just be equal to the tan inverse of omega rc plus pi, right? So that's the generalized solution that we have. All right. I have here that this part, or our omega rc, is very large for practical circuits, right? So I can make this infinity. When this is infinity, it makes that part, right? Tan of infinity, that's 90 degrees, or pi by 2. So we have minus pi over 2 plus pi, and that's just a half. So if you notice in the expression where we have our 90, right? It coincides with the 2. Or 90 degrees, that is. Sorry, where am I? All right, so that's how we get the Vm sine omega t sine theta is equal to Vm. All right, so we can now look at omega t when it's 2 pi plus alpha, right? Why are we doing that? Just to, at this point, if I remember this, one cycle, this is what, 2 pi, right here, up to right here, that's 2 pi, but we're adding alpha here. So 2 pi plus alpha, we're going to now substitute that into the equation, and it comes out to be equal to this. And we can solve this numerically. It is quite involved. So for these types of questions, I'd more likely tell you what the values of alpha and theta are equal to. All right, so how about the maximum and minimum voltages, right? You would have seen from the graph that the minimum voltage occurs at 2 pi plus alpha, right? Look, the cycle over 2 pi plus alpha, that's where it is a minimum. All right, so the ripple, as I mentioned earlier on, is also the difference between the maximum and the minimum voltages, right? So we can substitute the value for when omega t is a minimum. We know that minimum, that's going to be, maximum is V max, minimum we substitute, right? So it's just Vm sine omega t plus alpha. So this is the difference you will be calculating, right? So when you do that, you're left with this expression, Vm minus Vm sine alpha. And of course, let's make V theta equal to Vm and the theta equal to pi by 2. So our capacitor that would be used, it should be large such that the output voltage is constant, right? So your alpha is going to be approximately pi by 2, right? So you can determine this by setting omega t equal 2 pi plus alpha into the equation, right? So you're now going to substitute all of that into the expression here. All right, and you would have been able to approximate what the ripple voltage is equal to. When that is settled, this is the expression that you have resulted, and you could do some kind of series expansion, the Taylor series, expand this, and when the dust is settled, the ripple is just the peak voltage divided by the frequency multiplied by the resistance and the capacitor, right? So if you didn't quite get the mathematics, right, you need to know this part, right? That the ripple is just the peak divided by the frequency times the resistance times the capacitance. What this is telling us we can minimize the ripple by increasing our resistor or increasing our capacitance, right? So any of those two can be increased so as to realize a reduction in your ripple. Also, if the frequency is increased, then you'll be able to realize that reduction in the ripple. The current in the capacitor, right? We can express it like this, right? So C times the change in voltage with respect to time, and then we can substitute our omega t for the time, and it will look like this when you do the differentiation. And you'll recall that for the output, these are the equations that characterize the diode when it is on and when it is off. So you can do the substitution, right? So I omega c, right? You can now substitute these values in the expression, right? So how you do that? Your I omega c is equal to omega c dV output, the derivative of your output voltage with respect to time, right? So this is your output voltage. So you're going to find the first derivative, right? And this is omega c times V cosine theta. This is when the diode is on. And of course, it would be in this region between 2 pi plus alpha and 2 pi plus theta. And you do the same thing for when the diode is turned off, right? Just finding the first derivative, right? And of course, from the waveform, you would have noticed that the diode is turned off between theta and 2 pi plus alpha. All right, now for the peak diode current, right, that's just the sum of the current that will be flowing through the resistor plus the current that will be flowing through the capacitor, right? So if we go back and we look at this curve, right, so you can split this, right? So we have the two components, right? So IR and IC. Right, so here you can substitute the values, right? Now that you know what your IC is equal to, right? You can write that down. You set it equal to 2 pi plus alpha, make the substitution, and you will realize the expression for the peak current capacitor. All right, so how do you find that for the resistor, right? We simply make the substitution, same substitution, 2 pi plus alpha into the expression, right, for your current, and that's the Vm sine 2 pi plus alpha over R, and that will just be reduced to Vm sine alpha over R. So your peak diode current, right, just summing these two, the value for the capacitor and the value for the resistor, right? So this is for the capacitor over here, and this one for the resistor. Right, so this is the expression for your peak diode current. All right, so we can look at an example, right? So what kind of questions you could be asking this? Here we have a half-wave rectifier, has 120 volts RMS source at 60 hertz, and the load here is going to be 500 ohms. Your capacitor is 100 microfarad. You have to assume that your alpha and theta are calculated as 48 and 93 degrees respectively. So from this, you have to find the expression for the output voltage, the peak-to-peak ripple, and the capacitor current, peak diode current as well. All right, so this is a waveform. This is your alpha, and this is your theta. Right, so you don't have to use any numerical methods to evaluate alpha and theta as they are given to you. So you just need to substitute the values, right? So you will need the peak, so peak voltage. Here you are told that it is 120 RMS, so you can multiply by √2 to get the peak. And note that the angles that we use, you should convert them to radians. Right, so you'll have to get familiar with your calculator or you'll convert them, right? It's very simple, right? It's just the angle divided by 180 pi. That's how you convert. So for alpha, convert to radians, right? So theta 93, alpha 48, right? These are given to you. We convert them to radians. We need to calculate this part, right? Vm sine omega t, right? Because that is going to be in the expression, and we substitute the values. So in writing the expression, right? So this is actually the formula that we are using. Let me go back to voltage, right? This is what you're using for your voltage, right? So expression when the diode is on, when the diode is off. So that's why you're substituting to obtain these values. Right? So when you substitute, this is the equation you so formed. All right, any questions? Any questions? Did I put you to sleep?
Sir, not so far.
All right. We will stop here. But it's pretty straightforward. You just have to go back over and just get familiar with using the expression. It won't get any more difficult than this, right? So just understand the equation that governs the RC type load. The theta and alpha, I will always give them to you in an exam. You just need to substitute them and get the appropriate expression, right? So it's very simple. So we could also now calculate the ripple, right? Remember, the ripple is the difference between the maximum and the minimum voltage. So again, we use that formula. It's just the peak over FRC. We substitute these values and we get 56.7. And the capacitor current, remember we have the expression, right? So this is the expression, and all we are doing is making the substitution here to arrive at our expression for the capacitor current. And the peak diode current, this is the expression that we formed, right? To get this value, we just substitute the values and it comes to 4.5 amperes. Very straightforward. So in our next class, we will look at the controlled rectification. So in summary, what we have looked at in this lesson is the rectification as it relates to resistive loads and also to resistive capacitive type loads. When we look at just the resistive type load, we observe that there was no difference between the output voltage and current waveform, no phase shift, and this is quite expected. We then did some, we look at how we can determine the average output voltage and current, the RMS voltage and current in the resistive type load. We then look at the case where we have resistive and inductive type load, and we saw where there was a phase shift, very much different from when we have a purely resistive type load. We observe a difference in the current and the voltage waveform. And also, when the current goes to zero in the diode, right, we have that cutoff angle beta that is associated with this kind of circuit. We look at a method by which we can calculate our beta. That is the numerical method. It was mentioned, and I told you that we will be calculating our extinction angle beta using a graphical technique, and this I will introduce to you in the next lesson, right, in the tutorial session. How do we calculate beta? In that same circuit where we have resistive and inductive load, there's another unexpected occurrence. We saw where in the negative region there was a spike. Unlike in just the resistive type load, in the negative region it was just removed. That is expected. However, with this circuit, resistive, inductive, we observe a negative spike that goes to zero right at the extinction angle. This negative spike is as a result of the inductor in the circuit. The inductive behavior will resist or oppose changes. So as that voltage decreases, that negative spike is in response to that change that is taking place in the circuit. We then look at the resistive, capacitive type circuits, rectification circuits, that is uncontrolled. We look at the different waveforms, the voltage and the current, and the calculations associated with them. How do we find the peak current through the diode, the capacitor, and so on. All right, so we will stop here.
So, sir, you're gonna set up the canvas now for both industrial and